Okay, done. All right. Okay. So first of all, this is what we have discussed in last first sections. So we discussed what is meant by independence event and mutually independent events and pairwise independence events. Okay. So when n equals to 2, these two concepts are identical. So however, when n is larger or equal to 3, so it is not the same. Okay, so there is this pairwise is not equivalent to this. Okay, so once we have the concept of independence, okay, so we can have these two important results here. Let me get here. Okay, so pairwise independence does not imply mutually independent. Okay. We also discussed some of the examples to describe the demonstrated ideas. Okay, next will be the Borel-Cantelli lemma. We have two versions for it. So the first version will be when the summating of PAK is not infinity. So the probability of lim sub AK will be 0. Next, we need an additional assumptions. We suppose our events are all independent. Independence here means mutually independent. Okay. And the summations of all the probabilities infinity, then we can get the probability of lim sub AK is equals to 1. So this is what we so-called Borel 0-1 law. Okay, so like what we have discussed just now here, that is this feature. Yeah, why we call it 0-1 law. So this is the what we have discussed just now. When AI are independent, so that means we, I think this one, yeah. When A1, A2, and so on a sequence is a sequence of independence event, then we either the probability of limit superior an is 0, or the probability of limit of superior an is equals to 1. So that's why we call this is a law of 0-1. Okay? So we have discussed a proof for it. So some of the we have used a lot of important results like this. Okay, so one of the interesting properties will be this one. Okay, so we can actually use this Borel-Cantelli lemma to draw this conclusion. This is the one. For a fair coin, we can actually get infinitely many times of head, okay, as long as we keep on running the experiment. So for sure, we can get a head for some times. Okay, so it's actually which is consistent with our nature intuitions. Okay, so this is what we have. Okay, before we proceed to the next one, the independence of random variables. So let's go back to the independence of events. So this is the one. PA and B is equal to PA times PB. So this is a independence event. Okay. When we talk about ABR event, so we can also have the idea of independence random variable. Okay, so this is the case here. Okay, supposing we have two random variables x and y, we said that they are independent if and only if P of the pre-image of B under x and the pre-image of C under y is equal to this, okay? For all Borel subset. So this one can be extended to up to a sequence of xn. So this one also true for a sequence of independent events. Okay? Not events, random variable. Right. In general, this is what we can have. You can refer to our lecture notes here. Okay. So in general, that will be like this. However, it looks a little bit complicated. So I just demonstrate the idea with two of them. So, okay. So that is actually just let you know the meaning for the symbol here. So this is actually mean this. So we said X and Y are independent random variable if and only if this P of the pre-image of B under X intersect with pre-image of C under Y is equals to P of XB multiply P of X, Y inverse C. So this is actually intersection. So this one we most of the time we also put it as this way: P of X inverse B, comma Y inverse C. So that's a symbol that we have used here. When we put comma means we are taking the intersection of these two events here. Right. So in general, we can extend this into a sequence of events, which I'm not going to state out here. So it's just that we just extending here and extending here. So this is for independent random variable. Okay, next, because random variables, we have three different cases. So this is actually another topic. So random variable, actually we have also three different cases. So the first one, okay, we have a discrete random variable, okay, like what we have discussed in chapter 2. We also have a continuous, maybe we say absolutely continuous, but most of the time we won't say, we just say continuous, okay, absolutely continuous. And also this is something mixed. Okay. So this is not a very common one. So that's why we are not going to consider it. So this is not common. Okay, so that's why here we will discuss here. Okay, because not common, it's very rare to happens in your experiment, and so that's why you don't have to consider. We not consider. So we are not considering this case. So we only look at these two. Okay. So once we have a discrete or continuous random variable, then we can look at what are the easy criterion for us to test whether this is independent or not. So for discrete, when you ask when will there be independent? Okay, or maybe we will share this is any simple criterion to judge whether it is independent or not. Okay, so same as this. When discrete, can we have any simple criterion to check whether it is independent or not? Same as the continuous case. Any simple criterion to check if they are independent. Okay, for discrete and continuous case. Okay, so then we do have actually, so this is the one here. Okay, so for discrete random variable, so you can look at it. If we have two discrete random variables x and y, so they are independent when P of x equals to small x, y equals to small y is equal to product there. So it's a very simple way to test it. Okay? So likewise for continuous. Okay, this is actually our theorem 3.2.3 and 3.2.4 in our lecture notes. Similarly, for continuous random variable, so we have a simple criterion for us to check whether they are independent or not. I believe you should have seen them before in your undergraduate courses. So that is a simple criterion. So the joint density function fxy in the point xy, so it's fx x fy y. Okay, we can actually extend this idea to more than two. Okay, so you may look at the lecture notes here. Okay, so in general, that will be this and this. Okay, so however, I think the n equals to 2 is already enough to demonstrate the concept for it. Okay. So in general, when we come to the sequence of it, okay, in general, that's the case. In the general case. So we said that x1, x2, x3, x4, and so on. These ones are independent. Okay. Means so any finite subset of this random variable is also independent. Okay. So that's why we can extend the idea for an infinite sequence of independent random variable by using this. Okay, next we look at these examples here. So maybe I will verify up to here. So the second point you can do it yourself. Okay, so this is one example for and what do you call that? A sequence of independent random variable. Okay, up to infinity many of them. Okay, so let's look at how to construct this. Okay, one example. So supposing P is a uniform distribution on this sample space omega 0 to 1. Okay, so that means we consider an outcome will be any number in between 0 to 1, including 1. Okay, each point of omega has a binary expansions given by this. Omega is 0.x1, omega x1, and so on. So where each xk is equals to excuse me, either 0 or 1 here. Okay, so not showing this. Okay, what is the meaning for this? So let's look at here. Omega is this. So xk omega is 0 or 1. So just briefly look at these examples here. So just look at the idea for these examples here. All right. So we can always, let's say this is omega is 0 to 1, right? So which means our omega is always in between 0 to 1. Okay, here we write 1 is equal to 0.9999999 and so on. Okay, non-stopping. So we can actually that's the meaning of 1 here. Okay, omega is in between 0 to 1. So if this is in between 0 to 1, so we can write omega to be 0.1 digit D1, D2, D3, D4, and D5 here, and so on. Okay, here D1 is 1 over 2. This is 1 over 4. This is 1 over 8. 1 over, what is the next one? Okay, 16. And this is a 1 over 32 and so on. Okay, so this is a representative. But here, this DI is always 0 to 1 on here. We always take DI is 0 or 1. Okay, it's just like the binary representation for this. So I think I'll just give you examples here. Okay, for example, let's say if you look at 0.1. Okay, 0.1. So this can be written as 0.1, right? So 0.1 means 0.1000 and so on. So therefore, this is enough space. Okay, so this is actually 1 over 2. That's it. And it's supposed to be plus 0, 0. Okay, maybe forget about this. So here, another example, let's say 0.01. So what's the meaning for it? So this is equals to 0 plus 1 over 4. Okay, so that's the meaning of 0.01 here. So this is a binary representation. So which is actually 0.25 in our conventional sense. Okay? So another example, so let's say 0.1001. So what is this number? So it means half plus the second one 0, the third one 0 plus 1 over 16. Okay. Okay, I think one last example. So let's say 0.01011. What does it mean? So this is means 0 plus 1 over 4 plus 0 plus 1 over 16 plus 1 over 32. Okay, so that's the, we call it the binary representation for this number in between 0 to 1. Yeah. So that's the meaning for all this number. Okay, so if we represent in our conventional, what do you call it? So number system, that will be this. So that means actually this is means this one plus this one, so that will be 9, right? So 9 over 16. So this one will be okay. I don't know what's number. You guys go and calculate, right? That's the way. Yeah. So now you understand the meaning for it. So that means from here you can see for any number omega in between 0 to 1, we can always have such a binary representation. Okay, so that's the meaning for this D1, D2, and so on. So this DI is actually just taking two values, 0 or 1. So so that means in this case, then if this is our omega, so that means in this case, so this one means in this case, so our x1, x2, x3, x4, x5, and so on. So in this, x1 will be 1. Okay. So x1 will be 1, and the remaining will be all 0. So for this case, 0, 1, right? So that means x1 will be 0. This is 1 and 0, 0 for the remaining case, and this is 1, 0, 1. Oh, sorry, 0, 0, 1. Okay, that's the meaning for how we define the random variable x1, x2, and so on. Okay, for this number, so it defined as 0, 1, 0, 1, 1, and so on. Okay, so this is the meaning for this omega here. Okay, I hope you can get what's the meaning for this omega and how we can actually represent a number omega in between 0 to 1 by using this kind of a binary representation. Okay, so this is the representation for our omega. Okay, let's go back to here. So I think now you understand the meaning for this omega and x1 omega and so on. So okay, this either one. Okay, first of all, what we need to do is we need to verify all the xk are random variable. Well, according to here, xk takes only two values. Okay. So xk omega is either 0 or 1 according to here, right? So xk is the indicator functions. So when this indicator function, therefore it must be a random variable, okay? Because any function with a finite value must be a random variable. Okay? Okay, next will be this. The probability of xk equals to 1 is equals to half. Okay, in general, how to prove this is not quite complicated. In the general case, it's quite complicated. So I'm not going to look at how to prove this in the general case, but I just give you an idea why this is equals to half. Okay. So I just briefly explain the idea here. Okay, just to give you the idea. Okay, just the idea, but not the proof in the general case. Okay, so for example, just do it one by one. So first, y px1 equals to 1 is half. Okay, so why this is half? So you look at here. So it's not difficult. Just imagine this. When x1 is 1, so we must have omega must be greater or equals to half, right? So because when x1 is 1, so you may look at this example. So when this is 1, x1 is 1, x1 is 1, so we can always have a half here. So for this, when x1 is 1, I can have a half here. Half plus this, so this is actually larger than half. Okay, so this is easily, we can get this from here. Okay, when x is 1, omega is greater than half. And by our setting, here, omega is between 0 to 1, right? So that means then we can see this is always in between half and 1. So now if you draw a line here, okay, I think we don't have to do long. Okay, maybe like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, up to here enough. Okay, let's say if we draw this, so let's say this is 0, this is 1. So according to here, omega is always in between 1 and half, right? So we cut it half. So that means our omega will be always somewhere here. Okay, somewhere here. So from this picture, then you can see for these portions, we can always have omega is 1. So whenever omega belongs to this portion, x1 is 1. So whenever omega belongs to here means x1 must be 0, okay, because of here. And now if you look at the length here, 1 to half, so the length of omega must be in between here. So this interval, so that's why from here that we can see, so P of x1 equals to 1 will be the length of the interval here, the probability of half to 1. This interval, half to 1, right? And we are using the uniform distribution. That's why this is equals to half. Yeah, so that's explain this. Why that explain this part. Why this is equals to half. When k equals to 1, we can get 1. Okay. So how about the second case? So then y p of x2 equals to 1 is equals to 1. Why? So we can actually get the same ideas here. So x2 is 1. So we come back to our diagrams. X2 corresponding to 1 over 4. Okay. So that means we have to cut our interval into 4 parts. So let's say we cut into 4 parts here. Okay. So again, let's say this is 0, this is 1, this is half. So according to this setting, right, so you can see this interval belongs to the portion x1 equals 0. And also this interval is actually the event x1 equals to 1. Okay. Okay, when will this is equals to 1? So you can see we have 2 different cases. So let's say just an example. Let's say look at the first one. So let's say omega is 0.01. Okay, this one doesn't matter. So when this is 0, okay, so that means it will be here. Okay, so then this is 1 over 4. So that means you can see this green color omega will be belongs to this part. Okay, so that will be in between 1 over 4 to 1 over 2. Okay, this green color omega must be in between here. And so you can see this part will be belongs to x2 is equals to 1. Okay, so this part will be x2 equals to 0. X2 equals to 0. Okay, from here you can see. So that's another possibility is any other color. Okay, okay, purple color. So another possibility, omega is 0.11. Okay, this is 1. Okay, when this is 1, so that means your omega must be in this part. So this is 1 again. So therefore, it will be here. No, sorry. It will be here. Okay, because it's a 1 over 2 plus 1 over 4, that definitely will be more than 3 over 4 already. Okay. So therefore, you can have this is also the portion x2 is equals to 1. And likewise, so this is belongs to the portion x2 is equal to 0. So you look at these 2 parts. So that means in this case, then you can get this. So the probability of x2 is equals to 1 must be equals to the probability of either 1 over 4 to 1 over 2 or 3 over 4 to 1. So, and this is 1 over 4, 1 over 4. Therefore, this is 1 over plus 1 over 4. It ends up to be half. So this explains why this is half. So you can actually use the same process to get the probability of x3 is half, equals to 1 is half, and so on. Okay, so you just need to keep on bisecting this interval. Then you can get the same conclusions. Right, so this is how we can get it. The probability of pxk equals to 1 is equals to half. Okay, so I just show you how to get this conclusion for x equals to k equals to 1 and k equals to 2. The remaining you can actually obtain using the similar way. Okay, so this part, get this. Okay, now because of d1, d2, dn are either 0 or 1, so then we can get this is half. Okay, because this is either 0 or 1. So when 1 we get half, when 0 we also get half. Okay, so to verify this is an independence, I think this is a straightforward thing. So once you can get this thing, so the remaining are sort of like a straightforward calculation. Okay, so you can see omega belongs to this, x1 equal to d1 to this will be this, because here we already know this is a d1 up to dn, but this is don't know. So then we can see x1 is d1 up to xn is d1 is 1 over 2 power n. Okay, so this one we can get it. So, and also p is a uniform distribution. So if you multiply each of them, it'll be half. So this is actually n of them. Okay, so we have half. So then this is actually half multiplying half for n times. So you can see these two identical. So therefore, it must be independent. Okay, so this example just to show you that we can actually, that it is always possible for us to construct a infinite sequence of independent random variables. So, okay, so this is an example. So we can construct infinite number of random variable. Okay, next one, we have several results here. Okay, so function of independence random variables. Okay, okay, so this theorem looks a little bit complicated. So called the disjoint blocks of theorems. Theorem 3.3.1. X1 up to Xn and J1 up to Jm, and then blah 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 and so on. This event. Okay, so okay, so I just explained this idea for this theorem to you guys. So this is actually a very important result. Okay. So you don't have to look, you don't have to prove it. So you just need to aware of this result. Okay. So just give you the idea for these theorems. What does it mean by this theorem, or what can we talk about these theorems? Okay, just to give you this. So idea of theorem. What theorem is that? Disjoint block. Okay, before we look at the idea, just to let you know, this one just this theorem said that tell us that we can construct new random variable from combinations of several random variables. Okay, actually, as we can construct several. So we can construct new random variable with some existing random variable using, just need to do the combination of them. So this is a disjoint block theorem. So you just need to aware of this result, so we don't have to forget. Okay. So just to give you an idea, so for example, I just give you the idea for n is equal to 7, m is equal to 3. Okay, I think maybe, yeah, just the idea. So example, for the case n is equal to 7, m is equal to 3. So what's the meaning of n here? So this is the number of random variables. Okay. So what is the meaning of n? So this is the number of blocks. So n is 7, which means we're going to have 7 random variables. Okay, supposing we have, so let's say we have 7 random variables. Okay, T, U, V, W, X, Y, Z, 1, 2, 3, 4. Okay, yeah, supposing we have 7 independent random variable. Okay, sorry, I think I missed something here. It cannot be arbitrary. We can construct new independent random variable from a combination of several independent random variable. Okay, so which means if you have some non-existent independent random variable, so we can actually use a lot of methods to combine them to construct new independent random variable. Okay. So that's the spirit for this theorem. Okay, let's come back to our examples to demonstrate the idea. Supposing we have 7 independent random variable. Am I right? T, U, V, W, X, Y, Z. Yes, 7 of them. So we just simply divide it into 3 blocks. Okay, just cut into 3 of them. So let's say, okay, J block. Okay, let's say 7 of them. We make it 3 blocks. So let's say block number 1, J1, J2, and J3. J1 consists of maybe only Y. Y done. And this one consists of T, U, V, and T, U, V, and X. Okay. T, U, V, X. Okay, so the last one, 1, 2, 3, 4. So the remaining, so they must be, okay, so W and Z, 2 of them. So which means we cut into 3 portions. So this is very important. So all this must be disjoint. Okay, disjoint block. So what I mean by disjoint block, so that means I cannot have X here. So we cannot put overlapping X here. Okay, so that means there's no repeated random variable happens. Okay, so disjoint block, 3 blocks. So let's say we have a function. Data 1, data 2, data 3. Okay, let's say we have a data 1 is a Borel functions of y, right? Jy, so y on e. So let's say data 2 equals to a function g, which is in t, u, v, x, and theta 3 is G3WZ. Okay. So let's say this is a Borel function, then we can make a conclusion. These three must be independent as well. Provided G1, G2, G3 are measurable function. Okay, or we call it Borel function. Okay. Okay, this must be independent. So what we need to do is we just need to cut or separate this random variable into different groups. Okay, and after that, for each group, we just simply construct another functions. Okay, with the variable of all those random variable. Then the new function that are constructed using this method must be also random variable, and that must be independent. This is okay. So for example, if we consider this, right? So example, if we take theta 1 to be this one must be Borel function, or the standard one, so y, right? So let's say y power of 3 minus y. So this is the continuous, so must be random variable, right? So let's say we take another theta 2, or depends on 4 of them. So maybe let's say u square e minus x square minus t square and plus t multiplying log u. Okay, maybe not log. I don't like log. Okay. Maybe t multiplying eu again. So you can see this is also another random variable. So theta 3 depends on w and z. So theta 3, let's say now we have w over z plus e z w. Okay, let's say this. So in this case, so you can see all these random variables. So in this case, so these three, theta 1, theta 2, theta 3 must be independent. Okay, that's the idea for these theorems. So it depends on the number of independence for number of random variable, okay, and the number of block that you want to cut. Okay, what you need to do is just to ensure each block there's no overlap for each pair of block here. Okay, for example, you cannot have a repeated random variables. Okay, once you have block, you have partitioning this random variable nicely, and after that you just combining them using some measurable functions. Then the resulting function must be also independent random variable. Okay. Right, so we might not use it here. So this is what we so-called block functions. What I call not disjoint block function. Yeah. So okay, we are not using it at the moment. So in where? In chapter 5. This theorems. Maybe I just put. Okay. But anyway, it seems very natural. Actually, most of the time, so it's very natural. So you can just take it for granted. If we have a random variable, after certain combination of them, it must be independent. Okay, we can take it for granted. So, however, in mathematical formulations, before we make certain assumption, or before we draw certain conclusions, so we have to verify it first. Okay, so here I tell you that you can do that because of this so-called disjoint block function. Although we didn't prove it over here, someone has already proven this for you, right? So this is a so-called the disjoint probe functions. Okay. So the general statements, okay, it is here. Okay, so it looks very complicated, but the idea will be like what I have explained just now. Okay, next, again, as I said, as I mentioned just now, we have 3 different types of the random variables. Okay, as I mentioned here. So we have 3 different types of random variables. Okay, so the mixed one, the discrete, and the continuous one. And the mixed one is not common, so we are not considering here. There is a sort of like more advanced. First of all, it belongs to a more advanced setting courses. Okay. On the other hand, it is not so common. Usually, there's no much application to it, so that's why no point we go and study it. Yeah? So therefore, we focus on these 2 that we're going to deal with them most frequently. Okay, the discrete and the continuous one. Okay. Okay, so this is 2 formula here. Okay, the first one, we are dealing with the discrete case. Okay, supposing x and y are non-negative independent discrete random variable, then p of x plus y equals to n is equals to, we summating this. Okay, so this is for the case, discrete case. So this is our theorems. Three point three. Yeah. Okay, again, the proof of a general result, so I'm not going to do it, so I just prove it for a special case. So actually you can do it for the general one. Okay, so I look at the proof for n equals to 3. Okay, so you may extend it to general n. So we just look at n equals to 3, then you can, just to give you the ideas for it. Okay, now you can see when n equals 3, so x, y are independent. Okay, independent, so that means you can split them out. Okay, so n is equal to 3. So we look at it. So let's say x plus y. So we have x, we have y. So when x plus y is equal to 3, how many possibility can we have? So you cannot have negative value, right? So then first, when x is 0, y must be 3, right? So again, one other combination, when x is 1, y must be 2. When x is 2, y must be 1. When x is 3, y must be 0. So when x is 4, okay, minus 1, but because of this is always non-negative, right? So that's why we cannot have this case. So that's why only 4 cases here. Okay, so which means the event x plus y equals to n is a combination of 4 events here. X equals 0, y equals 3, and so on. Okay, so that's why then we can see it. The probability of x plus y is equal to 3 is actually equals to How should I write it? Okay, I think I can. Okay, I don't want to write it out, so maybe I can just x equals 0, y equals 3 plus, because this is a disjoint unit, right? So x equals to 1, y equals to 2 plus x equals to 2, y equals to 1 plus x equals to 3. Okay, yeah, I think it's better.
Doctor?
Yep.
Yeah, I want to ask, can x take negative value or not?
No, it's in our assumption here. We have said x and y are positive.
Oh, okay.
Not negative, not positive. So that's why we only can begin with 0. Okay. So it's already an assumption here.
Okay. Okay, thank you.
So plus px equals to how many of them? 0, 1, 2. Okay, 3 and y equals to 1, right? So this can, because of independence, right? So then we can have the px equals to 0, py equals 3 plus px equals to 1, multiplying y equals to 2 plus px equals to 2, and y equals to 1. Finally, px equals to 3, y equals to 1. Sorry, this is 0, not 1. Okay, so this is true because of we know x, y independent by our assumptions. We have make such assumptions here, right? Our assumptions are independent, yeah. So actually, I think you can look at this. So we can actually write like this. So this is 3 minus 0. This is 3 minus 1, right? 1 is 3 minus 2. 0 is 3 minus 3. So that's why we can actually use this k equals 0, px equals to k, py equals to 3 minus k. Right? So this is how we can get for the case n equals to 3. So you can see it's actually follow this pattern here. Okay. So in general, when you come to the general case, general n, right? So actually we can do it using the similar way. Yeah? So it's just that we keep on adding here up to n plus 1 times. Okay. So the idea will be exactly the same. So I think n equals 3 is already enough to demonstrate the idea how we can get this case, right? Okay, so this is for our discrete case. This is for our discrete case. So px plus y equals to n is equals to, we are summating n how should I say this thing? Okay, maybe what you can do is, let's say we do some things here. Let's say I put it n here. So is it a good way? This is n here. And okay, let's say we change this symbol. Let's say this is x. Then we have a small x. This is an x here. So this is for our discrete case. We have something like this. So we can actually, when we come to the continuous case, right, we can actually have a similar pattern for our formula. So let's say if you go to it, so then we can say f of x plus y. I think it's not a good idea. Forget it. How am I supposed to show you these things? Okay, n here. So you also get the n here. So this one, it becomes integrations. This is px, right? So then it becomes fx. And yeah, I think maybe I use another symbol. What symbol? Okay, let's say v. Okay, instead of k, let's say now I'm taking v. Fx, x equal to v, right? So that's why I have v here. And py, so it's actually, it's the row in the continuous one will be the, what do you call it, the marginal density function fy. So n minus v, right? So we can have so we have the same bit, n minus v. Okay, so this is n. Okay, I hope so. Okay. All right, so what I'm trying to tell you is, so actually you can, what you need to do, you just need to know one formula for a discrete case. So you follow a similar pattern, you can write out this. Yeah. Now we just need to change. So fix, okay, f of x plus y. Okay, instead of n, now we put it as I'm putting a wrong one. Forget it. I also don't know how to things how to change the things. Okay, maybe you look at here. I think x v minus x. Okay, maybe I put a formula here. Then you guys go and see the pattern. Oh, I think I'm using the wrong one. Yeah, this is dx. This is x, or maybe I should change this to x. Okay, so this is x. I change this to x. So this one I put it to be x. So this one I put it to be x. Okay, so the red color one I supposed to make it becomes v. So let's say this is v. This is v. This is v. Okay, forget about this one. Yeah, forget about this one. Then you can see actually it turns out to be the same formula here, right? It follows a similar pattern. Okay, so but it's only different will be on top there. We are using k here, but now we change it. Okay, you can see. So you just need to switch the symbol so that this is here. So f of x plus yv is equal to this. So because of x and y in a way symmetry, so you can sort it out. So you can go further. you just need to x to y, y to x, okay, then it turns out to be this way, f of x plus y v is equals to, so x to y, y to v, fy, okay, y fx v minus y dy. So that's why you can either put it in this formula or in this formula. Okay, either way. So, however, because in the lecture note, I think I'm giving this one in the lecture notes. Okay, so maybe if I put it in this representation, you might not get the pattern from here. So actually, not difficult. What you need to do, you just need to sort x to y, then you can get a similar formula. Okay, x to y, sort the x to y. So then you compare to here, then you can see the discrete case formula is actually identical to the continuous case formulas here. Right? Of course, this is a integrate over R. Okay, got it? So you look at our, so this is the theorems. Right, so this is the formula for the continuous case. Yeah, supposing x and y are independent and continuous. So we know when x and y are continuous, we can always find their density function. Okay, so now we use xy to construct a new random variable x plus y. So then the density function for x plus y, this new random variable, can be given by this formula, either this or this. Okay, depends on you want to put it in terms of x or in terms of y. Okay, right. So now want to get this. Right, so what we can do is we look at here. First of all, let's say if we put, let's say the proof. So let's say if we write v to be x plus y, okay. So then we have a fvt will be equals to, we do the integrations over v from negative infinity to 0 respect to f of v v dv. Okay, so this is this is what, okay, maybe I put it up put here. Okay, and also we know this formula, right? The relationship between this the density distribution function and the density function can be put in this way. Fv of this is actually we differentiating this. Okay. Okay, so now we can do this. So we proceed with this one to prove it. So f of vt can be written as, so this is actually equals to the probability of v less than t, less equal to t, and it can be written as p of x plus y less equal to t. Okay, we know this. Okay. So I think it isn't necessary this. Okay, yeah, the probability of x plus y less equal to t. So then it can be given by. So this is the region x plus y less than t. So that's why we have to integrate over the region x plus y less than t. Then we consider the joint density function fxy over here. So dx dy or dy dx up to you. Okay, next we have to use some calculus techniques to evaluate this double integral. So we look at the regions here. So this is the region x plus y less or equal to t, and of course this is a negative infinity. So we can here, if we look at a graph here, so let's say this is always our x, oh, sorry, this is y. So this is actually a calculus method problem. So this is y, this is x here. So x plus y less equal to t, so it's actually a line here. And because this will go to a negative infinity, so that means we assume that this thing could be extended to negative infinity here. Let's say we have this. So this is the line whereby x plus y is equal to t. So this is the t here, and let's say we can also go to the infinity. So this is the y is equal to negative infinity. So this is the x is equal to negative infinity here. So then this is the region that we are doing the integrations. Okay, this is a region whereby x plus y is less or equals to t here. So as usual, we look at our calculus technique here. So x plus y to t, so this is our left right hand side. So right hand side, then we can say this is x is equal to y minus t. So this is our left hand side. So left hand side for sure x is minus infinity. So for y, because of there are two ends here, so here we'll move up to, if we keep on extending this, so then we can see this will go up. So y will be go to positive infinity. So if you go down here, then y will go to negative infinity. Okay, for the two ends here. So from here, then we can evaluate our, look at this diagram. So then we can evaluate this integral that becomes like this. So then it ends up to be y is from negative infinity to positive infinity, and then x is from, so the left hand side, negative infinity up to y minus t. So for f of x and f of y dx dy. Okay, so again we have made use the idea here. So this one, because of xy independent, so we have f of xy is equals to fx, x and fy, y. Okay, again, now we want to animating the new variables here. So what we can do is we introduce a new symbol. So we are taking substitute x is equals to v minus y. Okay, so when x is equal to mu minus y, then when x is equal to y minus t, so if you look at here, so we substitute x is equal to v minus y, or v is equal to x plus y. Okay, so then we can have this. When x is y minus t, v will be t. All right. X plus y. X plus y. Oh, I think this is not y minus t, right? Okay, yeah, sorry. X plus y is t, and here should be x is t minus y. Okay, so then we should have changed here. So here should be t minus y. Yeah, then when x is equals to t minus y, so v equal to t. So when x is negative infinity, so v must be equal to negative infinity. And also I think it's clearly, so after the substitutions, so dx must be equal to dv. So after changing all this, then we can have this will become y is negative infinity to infinity. So then we have changing the parameter v from negative infinity to t. Okay, so here f of x b minus y, and then we have a f of y dy. Okay, now you can see this is independence of dx dy. This is independence of our not x anymore. So yeah, so you can see here is independence of y, then we can actually group them together. So this is y from negative infinity to positive infinity. Then we can just look at one group, sorry. Or actually, this is independent of y, so we can then, we don't have to, we can actually directly change it. Okay. So becomes v from negative infinity to t, and then y is negative infinity to here. So then we have f of x, v minus y, f of y, dy, dv. So what we can do is we can take this one as one particular portion. So, and this is actually, we go back to the early beginning here. So this is actually equals to fv of t. So we can put it in. So this is a fv of t. This is equals to this one. So then if we do the differentiations, then we can see, and fv of t is equals to, we just differentiating this respect to t. So then we differentiating this, then we only left this part. So that is, we do the y is negative infinity to infinity. So fx of v minus y, f y of y over dv. So this is actually the same formulas here. Okay, so this is the formula that, which one is it? I think this one. Okay, so this is how we can get this formula here. All right, I think we have about 15 minutes left. I think maybe a good time for me to stop here. So yeah, so this is the formula that we have discussed for the second section. So okay, first of all, we have two independent random variables, so we can use it to get a new random variable. In fact, this one we actually also use our disjoint theorem. So this one actually we are using this. So in this case, right? So we are having n. You can say that this is the case whereby n is equals to 2 and m is equals to 1. Okay, n is equal to 2 and m is equals to 1. So you have x1, x2. So in here, that means you can say g of x, y is equals to x plus y. So that means we only have g1 only. Okay, so m is 1. And we have 2, x1, x2, that means x and y. So this is actually one example for this disjoint theorem. Okay, we have two independent random variable, so we can construct a new random variable, this one, x plus y. Then we can have a nice formula to compute the distribution for this new random variable for the discrete case as well as the continuous case like this. Yeah. So there are two examples for it. I think it's good enough. Maybe we postpone it to next week. So this is one examples of continuous independent variables, and this is for two independent discrete random variable. Okay, we demonstrate how to apply these two formula to compute the distribution for the new random variables. Okay, right. I think I'll stop here now. You got any questions? Okay, maybe before that, so next week, so we will spend some time to look at tutorial 2. Okay, so we will look at tutorial 2, maybe 1 hour or 1.5 hours, depends on how many questions we'll discuss. So if you have any specific question that you want me to discuss, please let me know in advance. So you may PM me using Telegram or send an email, okay, to let me know the question that you want to discuss in next week. All right. Okay, I think that's it for today's. Okay. Any questions?
Doctor.
Yes.
For the example 325, the example x2 equal to 1. May I know the omega 0.01 and 0.11? How come is 1/4 to 1/2 and then union 3/4 to 1? The example.
Where is the example? Here, is it? Is it here?
Yeah.
No, in the first half or second half. Where did I discuss these examples? Just now, right? Where is it? Not here. Okay, I think it's here. It's here. It's here. Up there. Up there. Is it? Oh, wow. Where is it? Okay, why this? Right?
Why 1/4 to 1/2 and not 1/4 to 3/4?
1/4 to 3/4. Wait. Okay. Okay. Maybe we look at here. Okay. We look at over here. All right. So you just have to look at the events. What is the event? So when x2 is equals to 1, right? So x2 is 1. Just give you an example, then you will know. x2 is 1, so we can see example. So let's say our omega could be 0.11101, right? I'm just concerning with the one in the middle here, the one in the second part. Okay, as long as this is 1, that is what we want. Okay, get it? So this is one example. So let's say this is omega 1, omega 1. Let's say we took another omega 2. So it could be 0.01. Okay, what number? Okay, maybe 0.1. Okay, this 2. Got it? All right, so omega 1, so this is half, like I say, half, 1/4, and 1/8, and so on. So this omega 1 is like 1/2 plus 1/4 plus something else, right? So you get half plus 1/4. That means if you draw this diagram, so 0 to half. Oh. Yeah, I think maybe you are right. You are right. 1/2 plus 1/4, right? So 1/2 plus yeah, you can see okay, yeah, right. I think I'm okay. I'm right. Okay, 1/8. So this is 1/32, right? So we do not need this 1/8. Okay. So you can see 1/2 plus 1/4 or 1/8 is here. So yeah, we can put it easy. So 1/8 and 1/32 doesn't matter, but what we concern is we do have this 1/4, 1/2 plus 1/4 and plus 1/8. Okay, so 1/2 is up to here, plus another 1/4 is already here. So you additional 1/8. So your omega 1 must be somewhere here. Am I right? No, this is to be, sorry, this is not 1/4. This is supposed to be 1/2 plus 1/4. It should be 3/4. So your omega 1 must be here. Okay, so that's the reason why I'm saying that it must be belongs to this portion. 3/4 to 1. So this is how we get this portion. Okay, instead of this portion. Get it? Your omega 1 must be belongs to here. As long get it? When this is 1, when this is 1,
which means the can near to the 1, is it the possible for the omega 1?
Yes, is this part. I don't know where is it. The smallest can be 3/4. That means if your omega 1 is just 0.11, that's it. So that will be here.
Oh.
So if your omega 1 is 0.111111 and non-stopping, this is actually like what I said just now. Where is it? Like what I said just now. 1 is sort of like 0.99999. Okay. So if you have this case, right? So this is actually equals to 1. This is actually, what is that? 4/3. This is equals to 1. So I think this one you get a picture, right? So this is 1/4 plus, what is this number? 1/16. Am I right? So it must be, I hate this, 1/4 plus 1/16. Okay, when you're up to here is 1/4. you plus additional 1/16. So your omega-2 must be here, right? That's why I'm taking this portion and this portion. So that's the reason why I'm considering, where is it? Yes, right? Correct. This green color one or this one?
Oh, got it. Which means the first omega, the maximum is near to the 1/2, impossible over 1/2, right?
Yes.
Oh,
Yes.
Okay.
So that means if you want to look at the omega-2, right? So two extreme case will be like that. So your omega-2, two extreme case. One is 0.01. That's it. When you this is right, this is actually 1/4. That is here. That is here. Okay. For the blue color one. So let's say if you look at another extreme case, so 0.011111 and non-stop. Actually, you can use a series to look at it. So this one will be end up to be 1/4. 1/2, sorry. So that will be reached here. So that's why it cannot run too far away. It must be in between 1/4 to 1/2. Depends on whether the first one is 0 or 1. So if x1 is 0, it must be here. I don't know where is it. It must be here. This is when x, like I said, this is the x1 is 0 must be here. X1 is 0 and x2 is 1. Then it must be here. Get it? X1 0. This is x1, right? This is x1. This is x2. So x1 0, x2 is 1. So it must be into this interval. It cannot run away. X1 0 here, x2 1. And next, this is x1 is 1, x2 is also x1 is 1, x2 is 1. So it must be here. Must be in this interval. So that's why if you look at here, the probability for x2 is 1 must be the combination of this interval and this interval. So that's why it's 1/4 to half and 3/4 to 1. Okay. So the remaining is actually the same idea. It's just that it becomes more and more sub-interval. You look at it. When you look at k equals to 3, right? You have to cut again. Then you end up to be 8. Yeah, 8 of them, 8 sub-interval. I think it's clear right now.
Yeah. But
Okay.
doctor, I want to ask, if like let's say like x3 equal to 1, x4 equal to 1, is it any calculation we can know about the maximum of the omega, first omega, second omega? How to calculate?
What do you mean by that?
Like x3 equal to 1, and then we need to know the range, like this x2 equal to 1, the union
What I can tell you, how should I say it? What is you want to know the interval, is it? You're asking, you're asking about the interval, am I right? Okay.
Yes.
Actually, it's the same interval here, right? I think I don't like this one. Okay. Again, maybe okay. Actually, it's the same interval. You just remember, the first half is x1 is 0. Okay. You just have to remember this. Okay, so you have a big long interval. Okay, so 0 to 1. Maybe not too long. 0 to 1. Okay, so you cut into half. So remember, the first half is always x1 is 0, and this is x1 is 1. Okay, and after that, you cut into 2 pieces for each of them. So this is 1/4, 1/2, 3/4. Then you just have to know this part will be x2 is 1. x2 is 1. Is 2. And of course, here will be x2 0. x2 0. So when you go further, then it will be like that. Then you cut in another, become 8 of 10. Then you have this is 1 over 8, 2 over 8, 3 over 8, 4 over 8, 5 over 6, 7 over 8. Okay. Okay, then you can look at it. Here, this will be x3 is 1. Then here, x3 is 1, x3 is 1, and x3 is 1. So you can see this is 1 quarter, 1 quarter, 1 quarter, 1. No, 1 over 8, 1 over 8, 1 over 8. Then it ends up to be 1 over 2. So this is for k equals 3. K equals 4, you cut again. Likewise, you just carry on bisecting each of the sub-interval. Just like that. You're just repeating this process. Then you will get all the cases. Is this the answer that you want?
Yeah. Now, now got it.
You got it, right? So if you want to go to k equals 4, it's very troublesome. I'm running out of color already. So that means you have to cut again. You have to cut them again. Then you just look at each of the sub-interval. So this will be x4 equals to 1, x4 equals to 1. You combining all together 8 of them. Just like that. So I don't want to mess up my diagram. I better clean it. I think this is already nice enough. Okay. Great. So save. Okay. Any other questions?
Yeah. Sorry, I wanted to ask a question also.
Yeah, sure. Go ahead, Philip.
You know, when you the limit, like, you know, when you have limit of n to infinity, like when it's, can you take it in, and like when you have a probability and then in brackets you have lim n to infinity, can you take out the limit and put it back in freely?
Wow, good questions. I think. No, in general, no, you can't do that. You mean whether you can take out the limits or not, right? You mean this?
Yeah.
Okay. No, in general, though, this is not always true. So this one, not true in general. However, we have two special cases. Okay, we have two special cases. Then we ensure this is true. I can't remember which theorem is that. Chapter 1. I think at the end of chapter 1. So where is it? At the end of chapter 1. Where is my chapter 1? Where's my chapter 1? Hey, how come I don't have chapter? Okay, here. Okay, at the end of chapter 1. I think so. Two special case. We have just used the two results just now. Yeah, this one. Okay. Two special case, either when you have an increasing sequence of events. The second case, you have a decreasing sequence of events. So then this is true. Other than that, we are not sure. Okay. We're not sure. But increasing, decreasing, for sure, this is true. But other than that, we don't know. The reason is here. That is, just remember this. So when, what symbol I am using here? Cn, right? Okay. When Cn is increasing, okay, when Cn is increasing, when Cn is increasing, then I'm going to have limit for Cn is actually equals to the union of all of them. Okay, the limit is all of them. So by this theorem, what theorem is that? Where's my here? 1.4.3. So then theorem 1.4.3 tells us that P of the limit of P of Cn is equal to P of union of Cn, right? This is theorem of 1 point. So if we are using this symbol, yes, we have the phenomenon that you want. So then we are actually having limit of Pcn equals to P limit of Cn. So we can have this thing, but not always the case. Okay, this is when Cn is increasing. Then we have it.
I mean, because I was thinking like P is just it's, you know, like probability can be an integral, and when you have an integral, sometimes you can take the limb out, in and out under certain conditions.
In fact, I can tell you, if this is an integral, it's not true. In general, it is not true. Okay.
Yeah.
So we actually need some kind of the it have to satisfy certain type of the conditions. Yeah. In general, it is not true. Okay. The reason is true is because like this is like what I've told you guys. Actually, although I keep on mentioning, there's always certain subset which are not Borel subset. Okay. However, those subset will be very far away from you. You won't see it. Most of the thing in your eyesight will be Borel subset. So that's why, in a way, you can assume that this is always true. But in general, if you want to go to the more specific, in general, this is not true. Yeah. The reason you said you can always do this, right? Like what integrate is equal to this.
Yeah.
This is because of you always consider a very nice function. Okay. When f is a very nice function, for example, like continuous, what do you call it? Compact, continuous, blah blah blah. Then you have this. But if you have a very nasty kind of a function, this is not true.
But most of the time our probability distributions are nice functions.
No, that is more cases. But in probability, integration is okay. But when you come to probability, is no. Because of this is one need to be increasing. Actually, not necessary. Actually, you can actually most of the time the event is not increasing for most of the cases. Okay.
Okay.
So that's why this is not true in general. You remember only two cases that you can use, either increasing, the other one will be when I have a decreasing sequence, then this is true. Other than that, it would not be true in general. And in fact, other than that, this is not equal most of the time.
Okay, can I just check one more small thing?
Yeah, sure.
So when you have like the limb sub of an, for example, it's like intersection union of an, right? Is it the same as writing limit union of an?
No, in a way, yes, but you have to look at this. Because when you take union, right, you have to look at how you want to do the running index. So, for example, this is not arbitrary kind of the union. You have to fulfill these things. For example, if this is K, right? So it have to be what color should I use? Okay, so it will be K is equals to N, okay, to infinity. Okay, AK. K is equal to N to infinity, and after that, N will be another running index. N is 1 to infinity. So that's the meaning for it, N to infinity, K to infinity here. So you have to go through two different process here.
Yeah, so I can't write lim N to infinity of the union AK.
I don't understand I don't know what you said. Okay, for example, it must be like that. K running from N to infinity and next one, n is from 1 to infinity. So, but you can actually have things like that. For example, like a union, k equals to 1 to n equals to 1 to infinity, right? Okay, not always the case. Like you have an intersection union, that must be a lim sup. Okay? It depends on how you want to put the running index there. So that means in this case, so these two further are not the same. I put a big cross there. Get it?
Yeah. Sorry, I meant, you know, the first line, the intersection. Can you replace the intersection symbol with lim n to infinity?
Yes. For this case, yes. For this case, yes. Yes.
Which case?
Yes, this is true. You can say this is n to infinity for it. I have using this symbol actually.
Oh, it's the same thing.
Sorry?
That's the same thing.
Yes.
Oh, wow.
This is okay. This is simply because of I think we have to go back here. Where is my? I think here. Yeah, here. Actually, it's here. The reason is here. If you are putting lim sup, right? I am actually writing this this as our Bn. Okay, I am writing this as our Bn, and it so happens our Bn is a decreasing sequence. So therefore, I can write this one as an intersection of it. At the same time, I can also write this one as, because of this is a decreasing, limit n to infinity for Bn. This is true because of this is a decreasing sequence. I can write this. Okay, so yeah, this is actually my Bn. This fella is my Bn.
But it's not always we don't always know it's decreasing though.
If you put it in this way, it must be decreasing because it depends on how you construct your Bn, right? If you are constructing your Bn like that, it must be decreasing. If you're constructing your Bn in this way, it must be decreasing. Because you can see you're taking union of fewer and fewer numbers of An, right? So that's why your Bn is decreasing. It depends on how you construct the Bn.
Okay, so it's not true in general. It's only true when you use that theorem,
I would say that it might have certain cases whereby it so happens your An is neither decreasing nor increasing, but you still get the same property. It might have some sequence of events like that. But I don't know. It's just only that it depends on it. That means I cannot for sure to tell you the conclusion. Nevertheless, when we have a decreasing or increasing one, so I can always for sure. That's the conclusion.
Okay.
Okay.
Got it.
What I'm trying to tell you is, if without these two, I don't know. It might be yes or it might be no. I don't know. Okay.
Okay. Thank you.
No problem. Yeah, good question. I love this question. I hope it also clarifies some of the query of your classmate there. All right. So, you got any other questions? No. Okay. Good. See you guys next week. Okay. Don't forget to submit your assignment by next Friday. Okay. Okay, so see you. Good night. Have a nice weekend.